Hello, I'm Henderson, a PhD student in astronomy at The Ohio State University. Today I'll be telling you about my recent single-author paper titled Prospects for Characterizing Host Stars of the Planetary System Detections Predicted for the Korean Microlensing Telescope Network. Gravitational microlensing occurs when the light from a background source star is lensed by the gravitational potential of an intervening foreground star. The arising magnification of the background source, shown here, provides a tool with which it is possible to search for planets around lensing stars that are faint and/or distant. However, it is generally difficult to convert the observable microlensing parameters into the fundamental physical properties of the lensing system, such as the planet mass in the case of exoplanetary microlensing. In this paper, I investigate three channels through which the flux of the lens star can be constrained. Then, by combining a measurement of the lens flux with an estimate of the extinction to the lens, a mass-luminosity relation, and an estimate of either the relative lens source proper motion or the angular Einstein ring radius, the masses of both the planet and its host star, the lens, can be determined. The first method requires waiting for the lens and source to separate, and imaging the lens star once it is spatially resolved from the source. Here is an HST image of Macho LMC5, the first directly imaged microlens. The lens itself is the red star in the center of the frame, while the source is the blue star up and to the right. By waiting for the lens and source to separate, the light from the source star itself and any companions to the source do not contaminate the lens flux measurement. A second method involves measuring the elongation of the point spread function, or PSF, of the unresolved microlensing target, which consists of both the lens and source systems. While the lens and source are not fully resolved, the magnitude of the PSF elongation can be combined with the routinely measured flux of the source to determine the flux of the lens. Lastly, by taking high-resolution prompt follow-up photometry of the microlensing target shortly after the peak of the event, the total flux of the unresolved microlensing target, which is not spatially elongated in this case, can be measured. As shown here, this resolves out all stars not dynamically associated with the event to a high probability. Then, by subtracting off the known source flux, any robustly detected excess flux can be attributed to the lens star itself, assuming no bright companions to the lens or source. In this paper, I simulate programs to observe the planetary system detections predicted for the Korean Microlensing Telescope Network, or KMTNet, in order to characterize the host stars by measuring their fluxes. To learn more about the observational strategy and predicted planet detection rates for KMTNet, please see my earlier paper and video. I simulate H-band observing programs for the Very Large Telescope in Chile, the planned Giant Magellan Telescope, or GMT, and the James Webb Space Telescope, or JWST. Figure 2 shows the cumulative fraction of the lens flux precision attained using GMT to image resolved lenses 5 years after the peak of each microlensing event. GMT will be able to thusly measure the lens flux to 10% or better for 60% of systems. Here is the same plot for JWST, now 10 years after each event. For those lenses that JWST can spatially resolve from the source, the fluxes of all of them will be measured to a precision of 10% or better. I also investigate the effect that undetected companions to the lens and source stars would ultimately have on the derived lens mass. Figure 5 shows the cumulative fraction of the fractional difference between the true lens mass and the lens mass that would be derived if an undetected lens companion contributed blend flux that were falsely attributed to the lens. The curve corresponds to 3 sigma lens flux detections obtained via prompt follow-up photometry using JWST 3 months after the peak of each event. Only 12% of lens stars with undetected lens companions would have fractional mass differences greater than 50%. This drops to 6% of lens stars when considering blend flux contamination from undetected companions to the source. Here I have assumed that every lens or source star has a stellar companion, so these percentages would be further suppressed by the single star fraction. To conclude, I present the results of simulated observing programs that estimate the ability of current and future high-resolution facilities to measure the flux of the exoplanet host stars predicted to be detected by KMTNet. Over the next several years, these will be important channels for determining the mass of the planets hosted by these lens stars. Thank you very much for listening, and have a great day.